Double replacement reactions are unique in that we tend to divide them up into two subtypes. One of those reaction types are called precipitation reactions. The other type is called acid-base neutralization reactions. Precipitation reactions are a type of double replacement reaction where two reactants are dissolved in solution. And when they are mixed, they form one product that still stays dissolved in solution, but the other product that's made becomes what we call insoluble, in that it becomes a solid and it falls out of solution, or it precipitates and sinks to the bottom. In an acid-base neutralization reaction, it's a double replacement reaction where one reactant is what we call an acid and the other is a base. When they react stoichiometrically, the products form a solution with a neutral pH. The products are water and a salt. In other words, the acid and base neutralize each other, getting rid of the acid and base themselves and forming a neutral solution, pure water and salt. Reactions can actually be both precipitation reactions and acid-base reactions at the same time. Let's take a look at an actual precipitation reaction. Here is an example of a precipitation reaction between copper chloride solution and sodium phosphate. You can see that when the two solutions are mixed together, a solid falls out of solution. The products formed are a solution of sodium chloride, which is of course soluble in water, but a solid that can't dissolve, called copper phosphate. This is still a double replacement reaction, but we simply call it a precipitation reaction because of the insoluble solid it forms. We would still simplify the precipitation reaction much like the double replacement reaction. The only difference in the reaction in particle diagram would be that we would make sure we indicated the reactants and products were both dissolved in water using the AQ abbreviations, and the products with one having an AQ and whichever one would fall out of solution indicated by the S in parentheses. Let's go ahead and take a look at what our particle diagram and our reaction would look like for the reaction we did in the demonstration. Like in any double replacement reaction, we have a situation where partner swapping occurs. In this case, our cations, which are metals, copper and sodium, will swap places with each other. They will switch their partners, which copper has with chloride and sodium has with phosphate, and sodium will then bind with the chloride ions and copper with the phosphate. We can see it's like any double replacement reaction. The only difference in this case is that sodium chloride will be soluble and phosphate combined with chlorine will then become insoluble and fall out of solution. The overall process and particle diagram overview can be seen here. Now let's take a look at a demonstration of an acid-base neutralization reaction. In this demonstration, we have hydrochloric acid, HCl, that will react with sodium hydroxide on the right, NaOH. It's common for us to use universal indicator when dealing with acids and bases. Universal indicator is special in that it changes different colors when placed in different pH environments. Universal indicator turns red when the solution is strongly acidic, and it turns blue when the solution is strongly basic, or sometimes a purple, depending on the universal indicator you're using. The solution will also change different colors depending on the intensity of the acidity or basicity. When the solution is a perfect neutral, which should happen when a stoichiometric proportion of both acid and base are mixed, we should get a perfect green color, which would indicate a pH of 7. Here, I'm trying to get a stoichiometric proportion of both hydrochloric acid and NaOH mixed together to get that perfect neutral pH. which is what would happen in a neutralization reaction. And here you can see a perfect quantity of 1 mole of HCl was reacted with the perfect 1 mole of NaOH to achieve that water and salt product. This is an example of an acid-base neutralization reaction. Here we can see in the reaction, when simplified, what we have is what we would usually indicate as HA reacting with BOH, where A means acid and B means base. Acids are usually described as a substance which has a proton which freely dissociates or gets released when put in solution. Therefore, AH can be thought of as an acid. BOH we will think of as bases as substances that give away a hydroxide group, or OH, when put in solution. So this is why we tend to display reactions as HA plus BOH being acid-base reactions. When a neutralization reaction occurs, HA reacting with BOH, we produce HOH, which is the combination of the H and the OH from both the acid and the base, creating water. And since this is a double replacement reaction, therefore, the A and the B combine with each other to form what we call a salt. Since what we've produced is just pure water and a salt, we have neutralized the acid and the base, which is why we call this an acid-base neutralization reaction. And it's also a double replacement reaction since we've just had a partner swapping occur between the HA and the BOH. Let's do a quick review of acids, bases, and pH just to make sure we can easily identify an acid-base neutralization reaction. Remember, when we see acids, what we're looking for in the chemical formula is for it to start with an H in most circumstances. HCl, HF, HI, HO2, CH3, H2SO4. These are all acids that we learned when naming substances. They all have pHs of less than 7, and they turn universal indicator, or litmus, red. Bases, for our purposes right now in the class, this will change later on, but don't worry about it for now, have what we call a hydroxide group in the formula, or OH. These substances will therefore have OH in their chemical formulas. The OH will always come second in the chemical formula because it is an anion. Substances like NaOH, KOH, LiOH, and MgOH, subscript 2, and calcium OH, subscript 2, because these are group 1 and group 2 metals that combine with the hydroxide group to form the base. Bases always have a pH of greater than 7, and they turn universal indicator in litmus blue or sometimes a purplish color. Let's go ahead and look at the particle diagram and reaction for the reaction between hydrochloric acid and sodium hydroxide that we saw in the demonstration. So here we have the reaction between hydrochloric acid and sodium hydroxide. Remember, this is a double replacement reaction, so we'll see a partner swapping occur. The hydrogen, which is the cation for HCl, will switch places with the other cation of the other species, which is NaOH. As this partner swapping occurs, we now form pure water and a salt, in this case table salt. We now have a completely neutral solution of water and a salt. Again, why we call this an acid-base neutralization reaction. Now we'll take a look at the overall reaction and particle diagram. We remember that we have a red-looking solution if we have indicator in it, mixing with a blue-looking solution with indicator, an acid and a base. When mixed, make a pH 7 solution, if we have a universal indicator, that solution will turn green, producing a perfectly harmless saltwater solution.